Hello, I'm going to review some of the internal forces concepts and talk about shear moment diagrams. In structural analysis, it's very important to determine not just the external forces due to support reactions, but also the internal forces acting within the body in order to make sure that later on you use the appropriate materials that will resist these internal forces and they won't fail. So you won't have a beam that's cracking in those points where you have maximum forces of either normal, shear, or moment. So the way we do it is use the method of section. So in this cantilever beam that we have support reaction, and then we cut this section AA. And of course, if you assume this notation, the normal force on this, then in the opposite section, just like we did in process, you have equal magnitude but opposite direction. Here we have the shear going down, so in the opposite section, uh, it goes in the same magnitude opposite direction, and the same for the moment. So let's define these forces. So the normal force is perpendicular, so this is your cross section. So the normal force is perpendicular to the cross section, and then the shear would go parallel to the section or tangent. So tangent, parallel in this case, and then of course the couple moment or bending moment, and we'll see why it's called a bending moment in a minute. So this is very, very important. This is the positive sign convention that we'll use. So the positive normal force creates tension. The positive shear creates clockwise rotation. So you can see this clockwise, and then the bending moment, which will tend to bend the segment in a concave upward manner, or what I mentioned in class, the smiley face. Whenever we're in 3 dimensions, it's a little different, although we're not going to be developing the shear and moment diagrams for 3 dimensions, but I want you to take a look at this. So you have here the area. In the case of the area, so you only have one normal force because there's only one force that's perpendicular to the area. But then you have shear forces, in this case in the Z and the X component. You won't have shear in the Y component. And then in terms of the moments, X and in Z, you have bending moments. They bend the area. But then you have a torsion moment that is a torsion, creates a torsion along the length of the structural element. So they're moments, they are all either moments, but you have 2 bending and 1 torsional moment. In the last class, we saw this example where we were calculating internal forces. In this case, we saw how in the case of this beam, and I'm not going to redo everything, but this here was 5 kilonewtons. We first determined the support reactions, and then here we have point B, okay? So we have the shear here, the moment, and let's call it B, moment in B, and then the normal force in B using the notation. So what we did was sum of the forces in Y equals 0. And so we had 5 kilonewtons minus VB equals 0. So VB equals 5 kilonewtons. So that's how we did it. And then in the case of the moment, we do sum of the moments at point B. So we go to that specific area. Okay, and then we have AY times, in this case, the distance here forgot included. It's 3 meters. AY times 3, and this is a negative moment, plus MB equals 0. So MB equals here we have that 5, so 15 kilonewton meters. Now, if we go to point C, then it's a little different, right? So we have here the 5 kilonewtons, and I'll just do 1. Now, at point C, we're like to the right-hand side of that expression of that point B, so he's 3 meters. Again, we do the same notation. This is C, this is MC, and this is NC. In this case, NB equals 0 because there's no any horizontal forces. So we follow the same notation, but now you're going to have a different value if you are before the 6 kilonewton force or after. So we're calculating at a specific point. So in this case, I'm going to go through real quick through this, and remember, if you have any questions, you can pause the video. So we have, in this case, a distributed loading of 3 kips per foot, and you have to determine the internal forces at point C. So then you take an imaginary cut at that point. In this case, it doesn't matter if it's before or after because there's no forces right at that point C. And then you need to decide which more is convenient for you to solve. Of course, sometimes, just sometimes, you don't have to determine the support reactions, but in this case, you have a support reaction here, here, and here. However, there's no horizontal forces, so this here will be 0. So what you can do is you can even go from calculate the support reaction By. You have AY by calculating the moment about AY and then getting the support reaction, and then you automatically will have this. So you can use either the left or the right hand side. Okay. So we need to determine By, so we determine the support reactions. And whenever we solve for the distributed loads, remember we have it as 1, so it would be 6 feet times 3 kips per foot. So the foot eliminates, so you have the 18 kip area under the distributed load. And then applying the equilibrium equations of equilibrium, then you get your support reactions. Okay. So once you determine one side, you can say, okay, I'm just going to use that side, and then work from left to right or right to left, depending on what it is. But again, remember, in this case, you use the right hand. This is the one that will make it rotate clockwise. And then in this case, they didn't use the notation that we're supposed to follow. It was supposed to be like this in tension, okay? So, but let's just look at it because in this case, it doesn't matter because that normal force here equals 0, okay? So then you do your equations of equilibrium and you get your 6 kips and a moment of 27. Practice this one on your own, and in this case, this is one of those cases where if you cut here and then use the right hand section, you don't have to determine the support reaction. So you can go from right to left. Now keep in mind, now the distributed load, you need to do what? Calculate what is this height here, and you can use similar triangles. So you have here 1200, and here you have 3. So the relationship is that you have 1200 newtons per meter by 3 meters would be the same as this at point C to 1.5 meters. So then you can calculate the height of the reaction here. And I did not calculate this, but that would be equal to 1200 times 1.5 divided by 3, so this is 600 newtons per meter. So then this is what you have here, 1.5 meters, and then the height here is 600 newtons per meter. So you need to substitute this by the load, just the point load, and it would be the area under that triangle, which is 1/2 base times the height. You have an area of 450, so this is 450 newtons. And then this would be located at, here we have at 1 meter. Okay. So basically then you have now this point load, which is 450 newtons. Oh no, this is 1 meter from here. It's 0.5. Okay. This the whole thing is 1.5, so it's this 1.5 meters. Okay. So here's 1.5 and this one. And so here we have the shear, the moment, and the normal force. So then you just calculate those expressions. Okay, so now we have to look at equations and diagrams for beams, because this is a very important tool that you'll be using quite often in your rest of your structural courses. So it's an example of a shear and moment diagram. So what we do is develop the diagram so that with the diagram you can see each one of those where are the internal forces. Okay? So you have here the shear diagram, and this is the moment diagram, and we'll explain a little bit. So as I said, we're going to do the shear and bending diagrams, and we can use the method of sections, like we said, and then determine a mathematical expression for the internal shear and moments. Rather than looking at a specific value, we'll develop the expression as a function of the length of the beam. And I mean, it could be a column as well, so the concept would be the same. And the procedure is to determine the support reactions, then specify coordinates of x, having the origin at the beam's left and extending to the regions of the beam. Section the beam at a section X and draw the free body diagrams. Make sure you use the positive sign convention. That's what we mentioned. Positive shear, positive moment, and positive normal force. You'll calculate the shear by summing perpendicular beam axis, and calculate the moment by summing moments about the section end, and then you plot the shear versus the distance and the moment versus the distance. Okay, so we need to plot those diagrams directly below the free body diagram of the beam. So what I want to do is one example. I don't know if you had time to see this during class or not, but this is a simple example, so that if you don't understand this, then you need to review again some concepts. So here we have the shear and moment diagrams for this beam, and one thing I'm going to do is, I mean, the support reactions, it's like an homogeneous beam, and you have 5 kilonewtons. It's in here 2.5 kilonewtons. It has to be split 1 kilonewtons, and if you don't believe me, do the moment and summation of all the forces. So let me write it here. So this is 2.5 kilonewtons, and this is 2.5 kilonewtons, and no normal forces. So let me do this, and usually what we'll do is kind of partition all this. This is going to be my shear, and I'm going to draw my moment here. So this is, and again, I'm sorry, it's not perfect, but anyway. let's take a look at this first section of 2.5 kilonewtons, and then here I have the beam, right? So before B, okay, so I don't have the 5 kilonewton force, and of course then I have to follow the notation for the shear, for the moment, and the normal force. So when I do this expression, if I do some of the forces, let's do some of the moments, and I have some of the moments, let's call this point B, and it's to the left, some of the moments of B, and it would be to the left, and then I have my positive notation, then it would be as a function of the distance, okay, x. Then we have 2.5 times x, and this would be a negative moment plus moment at point B equals 0. So the moment at point B would be equal to 2.5x. Okay, and then for the sum of the forces in y equals 0, I have 2.5 minus v equals 0, so v equals 2.5. Now I see that the sum of the forces here do not depend on the distance, and so it's 2.5. So I'm going to draw this constant, 2.5. And usually we shade the area. Okay? Now, the moment here is 2.5x. So this is like an equation of the expression y equals mx plus b. So it's like a line with intercept 0 and a slope of 2.5. And when x equals 2, then the moment is 5. So I know that starts with 0 because that's the intercept, and it's a line with a slope of 2.5, and when I am at x equals 5. So you have an expression, and this is 5 kilonewtons meters. And so this is my shaded diagram. So as you can see, I have identified the equation, and I notice that it's intercept 0, and that has a slope of 2.5. It's a positive slope. And then at x equals 2, and I just find what is the moment. So now let's take a look at the second part, to the right of B. Okay, let me do it a little higher so we can. So now, to the right of B, I'm having those 5 kilonewton force, and then I have here my 2.5, and then I have here my distance of 2 meters. Okay. Again, I'm wanting this as a function of x, and here I have my normal force, which is 0, then I have my v, and then I have my moment. And remember, this is now to the right of b. So I can put a plus or a minus sign depending. So let me put here, this was to the left, and that one here is to the right. Okay, so sum of the forces in y equals 0, and so I have 2.5 minus 5 plus b, and then I'm now to the right hand side, and that's it, that's all I have, right? So I have minus 2.5 plus b equals 0, so this is minus v, this is minus v, so vb equals negative 2.5 kilonewtons. So then to the right, it goes from 2.5, and now I have negative 2.5 kilonewtons. Now I know that there's nothing between here and the end, but then when I get to the end, it's 2.5 positive, so it'll go back to 0. So things start in 0 and end at 0. So here is my shear diagram completed. So now let's take a look at the sum of the moments. So sum of the moments at point B, and I'm to the right, equals 0. So I have, and this is very important to follow through. So I have the also the sum of the forces. So I have let me put it here. 2.5 times x, and in this case it's negative, plus, then I have 5, and the distance, this distance to the right of 5, then it would be here x minus 2, and then plus the moment equals 0. So what we have here is 2.5 minus 10 plus m equals 0. So the moment, the equation for the moment, and this is, let me put this, would be 10 minus 2.5 x. And then again, this is the same type of expression where you have y equals y, intercept and slope. So I know that this is a negative slope. So when I substitute here at x equals equal to 2, I have to have a moment equal to 5, and that makes me, understand or confirm that this is correct. And whenever x equals 4, then the moment has to go back to 0. So if you do those calculations, and then I know it's a negative 2.5, so it comes from here and then goes to 0. So here I have the moment diagram. So that really explains moment and shear diagram. Remember, starts at 0, ends at 0, and we're going to see the relationship between these areas and these other areas. So make sure you understand this example. Okay. Now, in order to do these diagrams, we did a lot of calculations, but you can make some shortcuts whenever you understand well the relationship between the distributed load and the shear, if you have a distributed load, and the shear and moment. So whenever you have a distributed load, look at this here. And this is in differential form, but it applies for anything. So this v dx is like delta v over delta x, which is like the slope. Okay? So what it tells you is that the slope of the shear diagram, whenever you have a distributed load, equals to this, the distributed load itself. Okay? So the intensity is here. And this is in shear, in differential form. So this means that the change in shear equals the area under the loading curve. Because when I look at this expression, look at this minus Wx times delta x, this is the area under the curve. So keep this in mind, the change in shear equals to the area under the curve. So whenever you look at the change in shear from point B to point A, this difference is the area under the loading curve. Okay, we'll see that in a moment. The relationship between shear and moment. Okay, So in the case of shear moment, look at this. The change in moment over change in x equals the shear. Okay? So the slope of the moment diagram, which is this, is going to be equal to the shear. That's number one. And then when I look at this expression, the change in moment, which is mb minus ma, would be the area under the shear diagram. Okay, so those two things are very important. So just make sure you memorize those. So this would be an example of the common loadings. You have here this loading, and the shear diagram, we already saw how it's constant and then it decreases, right? So there is no distributed load here. So there's no change in shear from here to here, no change in shear from here to here, because this equals 0. There's no change in shear. Now, the moment diagram, it would be this area under the curve. So whenever we look at the change in moment here, would be the difference in area under the shear diagram. If you have case number two, you have the moment here. So you have a moment, you don't have any distributed load, so there's no change. Now we look at the moment diagram. It's going to be constant because there's no load. Same thing here, because you don't have any load, you only have that moment. Okay? So then here, now we have a distributed load. And look at this. dv over dx equals the negative w. So the change in shear from this point to this point is going to be equal to the area under the curve. So dv equals minus w times dx times loading times the distance. So this change in shear is going to be equal to the area under the loading curve. Okay? And then we look here, and these are the cases that are different, right? Because now you have kind of a curve here, and just remember what is the shape? It has this shape here. So then the change in moment is going to be equal to the curve under the shear, but then in this case, it's not a straight line. Okay? In this case, now you have a distributed load that increases. So when you look at the shear, of course, is the change from this point to this point is the area under the curve, and the way the shape between the 2 points is different. Now it's shaped like this. And then the same here for the moment, and now whenever it decreases, this is the change, but it goes in this form. So the moment, you always have this shape, okay? Concave down. And then this here is straight line, and then concave down, and then concave up. So this is the only case that is concave up, okay? So let's take a look real quick at this example, the shear and moment diagram. And as I said, first calculate the support reactions. And this is fixed support. And the normal force here is 0 because there's no other forces. So the first thing is the support reactions. So whenever we look, and you can watch this video as many times as you need to. So I'm looking at this point here, that is the 2 kilonewtons, and I have, this is my 0, and I go from here to here, but there's no distributed load, so there's no change in the shear. However, when I get to this point, now there's a distributed load between 2 and 4. And the area under the loading curve would be 1.5 times 2, and it's minus 3. So this minus 3 means that the change in shear between 2 and 4 is a minus 3. So VB minus VA equals negative 3. That's the change. Okay? So then I know what shear I started here with, but then I can calculate the shear at point B, which is VA plus that change. Okay? And then that change, which is minus 3, I add to this minus 2 plus minus 3, it's minus 5. And I get the shear. So remember, if there's a distributed load, the area under the distributed load gives me the change in shear. And I know that it's a straight line. Okay? So now I need to draw the moment diagram, and this is what I know about the moment diagram. And then what I need to remember is that the change in moment from point A to B, or in this case from this point 2 to 4 meters, is the area under the shear diagram. Okay? So in this case, the area under the shear diagram here is 2 times 2, which is 4, and it's negative 4. So I know that it goes from 0 to negative 4. And then from negative 4, I want to know how far down it goes. So I have here the area under this moment diagram. I calculate the area under that diagram. So it's minus 2 plus minus 5 divided by 2 times 2. And that's minus 7. So I know that then minus 4 plus minus 7 gives me minus 11. And I put the point here. Okay? So then I know that the slope, I mean, in this case, is a straight line. But here I know that there's a curve. And if I go back to these expressions, then I know that there's going to be a curve on the shear diagram. You can see it here. Okay. So if you want to know if it goes up or down, what you can do is just look for a point in between and then put a point. If you do it more or less to scale, then you can know it. Okay. So I hope this helps, and then practice, practice is the only way to get good at this. So this slides will be in Blackboard, so I encourage you to practice this example since we have the answers here.